If you've ever sat by the window during takeoff on a long-haul flight, you may have noticed something unsettling. As the aircraft climbs and hits turbulence, the wingtip doesn't stay still, it rises, it flexes. On some aircraft, like the Boeing 787 Dreamliner, the wingtip can move up several feet from its resting position. But if you look at a small regional turboprop, the wings barely move at all. And if you go back and watch footage of a Boeing 777 wing being tested on the ground, engineers bend it upward until it almost touches over the fuselage. So the question is, why do some aircraft wings flex so dramatically while others stay rigid? The answer is simple. In aviation, almost nothing is random. Even the amount a wing is allowed to bend is the result of a deliberate engineering decision. Every wing's flexibility is a compromise between strength, weight, aerodynamics, and survivability. To understand why wings flex at all, we first need to look at what a wing actually does. A wing generates lift by shaping the airflow above and below it. As speed increases, lift increases, and that lift pushes the wing upward from below. The fuselage, meanwhile, pulls downward under its own weight. This creates a bending force at the point where the wing meets the body of the aircraft, known as the wing root. The wing isn't a solid, unmoving block. It's built to flex, because a wing that couldn't bend at all would eventually break. The first challenge, load distribution. An aircraft wing must survive enormous forces during a single flight, from the initial rotation at takeoff to violent gusts at cruising altitude. If a wing were built as a completely rigid structure, every gust of wind would transfer its full force directly into the wing root, the weakest connection point on the aircraft. Engineers solve this differently. By allowing the wing to flex upward and absorb sudden loads, the structure spreads that force out over time instead of receiving it all at once. This is the same principle used in the suspension of a car, where a spring absorbs a bump rather than transmitting it directly into the frame. A flexible wing acts as a natural shock absorber for the entire aircraft. Why modern airliners are built with highly flexible wings. Modern wide-body aircraft like the 787 and the Airbus A350 use large amounts of carbon fiber composite in their wing structure. Unlike traditional aluminum, composite materials can flex significantly further before reaching their material limits. Because these materials can bend more without weakening, engineers can now use less structural material overall, while still meeting the same safety requirements. This directly reduces the aircraft's weight, and a lighter wing means better fuel efficiency across thousands of flights over the aircraft's operational life. In fact, this is one of the primary reasons composite wings have become standard on new long-haul aircraft. Every extra degree of flex the material safely translates into real fuel savings. There's also a structural benefit during turbulence. When a wing flexes upward in response to a gust, it briefly changes its angle relative to the oncoming air. This small change actually reduces the amount of lift the wing generates at that exact moment, which in turn reduces the load the wing experiences. In other words, a flexible wing partially cancels out the very force that's bending it. Rigid wings don't get this benefit. They absorb the full force of every gust directly, which means they must be built heavier and stronger from the very start just to survive the same conditions. Maintenance and certification are also part of the equation. Every commercial aircraft wing must pass an extreme structural test before it's certified to fly. Engineers mount a complete wing to a test rig and apply hydraulic force through dozens of actuators until it bends far beyond anything the aircraft would ever encounter in normal service, often past 150% of the maximum expected load. This single test can take years of preparation, since the same wing must also survive a separate fatigue test, simulating tens of thousands of flight cycles compressed into a much shorter time frame on the ground. Footage of the 777's wing test became widely shared because the wingtip rose over 20 feet before the structure finally failed, and that number wasn't an accident. It's the exact margin regulators require before a wing is allowed to carry passengers. That test isn't a flaw. It's proof the aircraft has enormous reserve strength built into a design most passengers never think about, and it's also the reason engineers can confidently tell pilots that turbulence, however uncomfortable it feels in the cabin, is almost never a genuine structural threat to the airframe itself. But despite these advantages, highly flexible wings introduce their own engineering challenges. One issue is fuel and system routing. Wings that flex significantly require fuel lines, electrical wiring, and hydraulic systems that can also flex with the structure without cracking or disconnecting. Engineers must design flexible couplings and looped wiring paths specifically to survive constant, repeated movement over tens of thousands of flights. Another challenge is passenger perception. Because the wingtip motion is so visible from certain window seats, some nervous flyers assume the aircraft is being damaged when in reality the wing is behaving exactly as designed. Our airlines and manufacturers have had to specifically address this in public education, because the visual of a bending wing can appear alarming even though it represents the aircraft working correctly. Why some aircraft still use much stiffer wings. If flexible wings offer so many advantages, why don't all aircraft use them? Smaller regional jets and older aluminum-structured airliners often use comparatively stiffer wing designs, and this comes with its own set of benefits. One of the main advantages is predictability at lower speeds and shorter routes. Regional aircraft spend more time in the turbulent lower atmosphere near airports, and a stiffer wing responds more consistently during rapid altitude changes typical of shorter flights. Another factor is manufacturing cost. Composite wings requiring precise flex characteristics are significantly more expensive to design, test, and produce than traditional aluminum structures. For smaller aircraft operating shorter routes with lower overall fuel burn, the long-term fuel savings from a flexible composite wing don't always justify the higher upfront manufacturing cost. There's also a practical reason tied to aircraft size. Smaller wings are inherently shorter, meaning they experience less bending leverage than the long wings found on wide-body jets. A shorter wing simply doesn't need the same degree of engineered flexibility to safely manage its loads, since the physical distance between the wing root and the wingtip is much smaller to begin with. However, stiffer wings come with their own trade-offs. Because they don't flex to absorb gusts the way composite wings do, more force transfers directly into the wing root during turbulence. This means the surrounding structure must be reinforced with additional material, adding weight the aircraft carries on every single flight, and that added weight compounds over the lifespan of the aircraft in the form of higher fuel costs. Stiffer wings can also produce a rougher ride during turbulence, since less of the gust energy is absorbed by the wing itself before reaching the cabin, which is one reason passengers sometimes describe smaller regional aircraft as feeling more affected by rough air than the wide-body jets flying the same route at the same altitude. There was also a historical turning point in this story. During the 1950s and 1960s, before advanced structural testing became standardized, several early jet aircraft experienced catastrophic wing failures that investigators eventually traced back to metal fatigue, a slow weakening of aluminum caused by repeated flex cycles over time. In several of these early cases, engineers had assumed that a stiffer, less flexible wing was inherently safer, since it moved less and therefore seemed less stressed. Investigators later discovered the opposite was often true. Wings that couldn't flex simply transferred every load spike directly into small stress points, and over thousands of flights, tiny invisible cracks began forming at those points long before any external damage was visible. These incidents fundamentally changed how the entire industry approached wing design. Aviation authorities introduced far stricter certification testing requirements, including the extreme bend tests still performed today, along with mandatory fatigue life calculations for every new aircraft design. Engineers also began deliberately designing wings to flex in controlled, predictable ways, rather than trying to eliminate movement entirely, since attempting to prevent all flex had proven more dangerous than managing it properly. As materials science advanced through the following decades, engineers gained increasingly precise control over exactly how much a wing should flex, and exactly where that flex should occur along its length. Modern composite manufacturing allows engineers to fine-tune flexibility down to specific sections of a single wing, something that would have been impossible with the aluminum construction methods of earlier generations. Looking at the history of wing design, one thing becomes clear: the way a wing bends is never accidental. Every flex characteristic is the result of a careful compromise between material science, structural survivability, fuel economics, and decades of hard-earned lessons from aviation history. That's why modern long-haul airliners are engineered to flex dramatically under load, while smaller regional aircraft are built stiffer for shorter, lower-altitude routes. In aviation, every design choice, even one as subtle as how much a wing is allowed to bend, is the product of precise engineering and decades of experience. And it's exactly these engineering decisions that allow today's aircraft to safely flex, absorb, and endure millions of flights around the world every single day.